Okay, so we are live now, and I have pasted all the links. And okay, so before we start, let me tell you a few things. Today is the deadline for week 9. I hope most of you have finished watching week 9 lectures as well as solving all the problems. And do submit your week 9 assignment by today. And there will not be any extensions for week 10. And week 10 deadline will be on Wednesday, 11:59 p.m. Okay, so yeah, so that's the other thing. All right, so let's begin. Week 10. Okay, so week 10, we have talked about complex numbers. Right, so those who have watched the lectures would know this. So we started with talking about natural numbers, set of natural numbers. And then we said set of natural numbers are not only the numbers. When we do subtraction, we kind of ended up getting some negative numbers, and we also included them and called the complete set as set of integers. And then when we divide two natural numbers or two integers, again we went out of this particular set and we called that set as set of rationals, right? So, and again, even after going into rationals, there were few numbers which cannot be represented as rational numbers, such as square root 2 and pi, e, everything. Right. So then we thought there are more numbers other than just the rational numbers. And finally, including that irrational numbers also into the account, we have defined set of reals. But are these the only numbers? So is every number is a real number? May not be. And this may not be as first introduced by Cardona. Okay, so he said real numbers are not only the numbers. There are few more numbers which are solutions of these kinds of equations. Right, so x square plus 1 is equals to 0. No real number satisfies this particular expression. Then he introduced complex numbers where he denoted I to be the solution for this particular equation, which is square root minus 1. So he said now we will use this and we will define solutions for all the polynomials. So now you don't have to worry about whether it will be real or not. All you can worry about is whether it is real or imaginary. So this when I say imaginary, it means that it contains this particular variable I. Okay, so for example, this x square plus 1 is equals to 0. If I say, if I look at solutions in real, where x takes real numbers, we will not have any solution for it. But in order to have a solution, or in order not to say any polynomial doesn't have any solutions, he has introduced this I and said for this particular, since it is a 2-degree polynomial, it should have two roots and both the roots are x is equals to plus I and x is equals to minus I. Okay, so now you don't have to worry about whether solution exists or not. For any n-degree polynomial, you will have n roots, whether it can be real or imaginary. So that is where it all started. Okay. And this I is called imaginary number. So I is the imaginary number. Imaginary. From the word itself, you can sense something, right? So In reality, you can never see this I. Okay, so formally, any complex number. Now, once this I comes into the picture, this will go, this will superset the set of real numbers. Right? Because how? Because complex number, every real number can be thought of as a complex number, that we will see now. But complex number is not something inside these sets. Complex number is something which contains all the sets. Along with that, you will contain more numbers in it. Now you can, so far, at least in till 2025, any number can be represented as a complex number. Okay, so any number. Now you divide any two complex numbers, you will still get a complex number. You multiply any complex number, you still get a complex number. You do any sorts of operations, you will still get a complex number. Okay. So maybe one day you can all, maybe one of you can be a new person, just like Cardano, who can design a new set, which is super set of complex number. You never know. Right? So it can happen. Okay. So now let's formally define a complex number and then say, or then see how real numbers are subset of this complex number. So any complex number, z is written as x plus iy. Okay, where this x is the real part of z. Okay, so the real part. So every complex number has two terms in it. One is x and one is iy, and you just have to add these two. Okay, so this x alone is called the real part of z, which is denoted as Re of z. Okay, so Re of z. So when z is a complex number, Re of z is a real part of z. And this y is called the imaginary part. Imaginary part of z. Okay, so real part, imaginary part. And imaginary part is denoted as Im of z. Okay, and this I you are seeing is what? One variable. Right, so that is what it is. So it's just a variable I which satisfies variable I such that when you square that, you will get minus 1. So I square is equals to minus 1. Okay. So this is the representation of a complex number. So now how real numbers are subsets of this complex number? Or why, when can a complex number be just a real number? So when y is equals to 0 or the imaginary part becomes 0, this one, when y is 0, you won't have iy. You will have only x. That means you will have only the real part of your complex number. And your real part is real number. Right? Just a real number. So when y is equals to 0, this set of complex numbers fall into set of reals. Or if y is equals to 0, z is a real number. In this way, so when y is equals to 0, you will have all the real numbers. When y not equals to 0, you will have, apart from along with real numbers, you will have new numbers like 1 plus 2y. When y not equals to 0, you will have a complex number. Okay, so I hope this is clear. And when you consider all these complex numbers together, that is called the set of complex numbers, which is denoted like this. The C, which is you collect all possible combinations like this, x plus iy, such that x and y are real. Okay, both of them should be real. And I square should be minus 1. Okay, so this is the set of complex numbers. Alright, so I hope you have studied all these things. This is just a recap to you guys. Okay, so few examples. 3 plus 20i. Okay, so when I say 3 plus 20i, you should be able to write down what is the real part of this complex numbers, what is the imaginary part of this complex number. So you can see you just have to compare. So this is the real part and this is the imaginary part. So real part of z is 3, imaginary part of z is 20. What if you have 15i, minus 15i? Just minus 15i, pure imaginary number. So for this, real part of z will be 0. So you will not have any real part. And the imaginary part of z is minus 15. Okay. And for suppose if we were given some 10,001, no imaginary part, then the real part of z will be this 10,001 and the imaginary part will be 0. Okay, so all three are complex numbers. All right. So that is about the introduction of a complex numbers. And once we know what complex numbers are, once we studied numbers, natural numbers and everything, the next thing we did is operations with those numbers, right? So we'll see that. So the next thing is operations on complex numbers. Okay, and first and foremost thing is how do you add two numbers, right? So how is addition done with respect to complex numbers? So if I have a complex number x1 plus iy1 and another complex number x2 plus iy2. Okay, so this is one complex number, this is another complex number, and I want to add these two complex numbers. So if I need to add this, you just treat this particular complex number like a polynomial with two terms. Okay, a polynomial as variable I. Okay, so x1, y1 are just the coefficients. So it's just a linear polynomial with respect to I, right? So when you treat it like that, how do you add two polynomials? Just add term wise. And here also we'll do the same thing. You just have to add the real parts together and the complex parts together. And if you add it, you will get x1 plus x2 plus I of y1 plus y2. That's it. This is how we do addition, which is okay to understand, right? And the second thing, once addition is done, even the subtraction can also be done in the same way, right? So if I have to subtract two complex numbers, all I need to do is subtract the real parts and subtract the complex parts, imaginary parts, and make it together. So I'm not dealing subtraction separately, but the way you do addition, just like that, you should do for subtraction also. Okay. And the next thing you should do is you should know is multiplication. Okay. And this is also in the same way. So once you treat this x1 plus iy1 as a polynomial of degree 1 with respect to I, then just like how you multiply polynomials, how you add polynomials, so everything follows. And there are some differences, I will tell you, but multiplication also the same. So x1 plus iy1 and x2 plus iy2, and I'm multiplying these two, right? So if I multiply, I have to multiply each term. I take the first term here, multiply it with the first term there, second term, first term, first term, second term, second term, second term, right? So if I do all those things, I'll get x1 x2 plus iy1 x2 plus x1 iy2 plus iy1 iy2. Okay. So when I multiply, this is what I will get. Now I will have I square also coming into the picture, which is when I multiply these two terms, I'll have I square. But what I know about I square is minus 1, right? So always remember in complex numbers, I is always square root minus 1. So when I do I square, I will have minus 1. Okay, so you have to do that substitution, that's it. So once you substitute that, you will see that when I square becomes minus 1, this term will also become real. So this is also a real part. This is also real. But these two will be imaginary. And we know how to add two complex numbers or two terms. And we'll add them and you will see the result will be x1, x2 minus. So I square will be minus 1. So this will be minus y1, y2 plus I of y1, x2 plus x1, y2. Okay. So these two, let's do a couple of problems related to these two properties, which will be very easy. So, okay, let's say a complex number z1 is 5 plus 4i and complex number z2 is 3 minus 2i. Okay, so we have two complex numbers. So if I add these two complex numbers, what will I get? Yeah. What will be the answer?
8 plus 2i.
Correct. So this will be 8 plus 2i. When I multiply, what will I get? Z1 times Z2. This will take a minute, but it is good to compute. So if I multiply these two, all I have to do is multiply 5 plus 4i with 3 minus 2i. What will I get? Okay, so you all can try this out.
Twenty-three plus 2 iota.
23 plus 2i. Okay, you can cross check, but that is true. Okay, so this is how we add two complex numbers, multiply two complex numbers. The next interesting properties or the operations will be this. One is called conjugation. Okay, so which we haven't seen in with respect to real numbers because conjugation is for complex numbers. So what does this conjugation mean is, so if I have a complex number z, which is x plus iy, okay, so conjugation means you just have to negate the imaginary part. So negating is if you have plus I, you just have to do minus I. So its conjugation is denoted as z and there will be a bar like this, z bar, which is equals to x minus iy. Okay, so if you have plus I, you have to do minus I. If you have minus I, you have to do plus I, which is like for z bar, its conjugation is z. Okay, so z bar's conjugation is z bar whole bar, right? So you have to do 2 times, and this will simply be z. Okay, so if you do conjugation twice, you'll get the same complex number. Or in other words, if z is complex conjugate of z bar, then z bar is complex conjugate of z. Okay, so it works both ways. Okay, so examples would be simply if I have 2 plus 3i, okay, its conjugation is 2 minus 3i. And if z is this is z bar. And if I have minus 2 minus 5i, its conjugation is
Minus
minus
2
2
plus 5y.
plus 5i. So you should not take negative for real part. Okay, so real part stays as it is. Only the complex part will change its change its sign. And how is this helpful for us? So now when you multiply z and z bar, what will you get? So you take a complex number and you multiply with its complex conjugate, which is like I have x plus iy and I'm multiplying it with x minus iy. So if you again do how you know how to multiply two complex numbers, right? So when you multiply, you will see that you will get x square plus y square and your complex number or that imaginary number variable I will go out, will vanish. And this will be a real number no matter what. Okay. And not only real number, it is also so x square and y square both are positive and you are adding two positive numbers. Right. So this will be a non-negative number. Okay. So a non-negative number which is a real number, we can always associate it to some distances. Right. So that is what we are going to do. So we will next define the absolute value of a complex number. Okay, so this is also a new thing. So in real numbers or in real world, we use this absolute value as just positive value, modulus. Okay, so when you have a real number, if I take absolute value of the real number, it will just give me just the positive part, right? So if I plus 2 or minus 2, if I do absolute, the result will be just 2 plus 2. Whereas in complex numbers, that is different. This is different. So this absolute value mod z is defined as square root of this z bar. Okay, so the square root of z bar is defined to be the absolute value, and this is square root of x square plus y square. So when we see the geometry, things will be much more clearer. Why I am saying this as a distance metric. Okay, but as of now, absolute value, this is how you should compute. You should take the complex number, you should take the complex conjugate, you should multiply them together and take the square root of it. That will give you the absolute value. Okay, so that is the next thing. And the final thing, we'll go back to the normal thing, which is division. How do I divide two complex numbers? So I have again x1 plus iy1 and x2 plus iy2. Now I am interested to divide x1 plus iy1 divided by x2 plus iy2. So when I divide two complex numbers, as I said earlier also, I need to have a complex number. And I know how a complex number will look. So I need to write this expression as some real part plus I into some imaginary part. Right? So I have to write it in this way. But the left hand side doesn't look that way. So what should I do, or what should I how should
I
I
think
manipulate?
rationalization.
Correct. So you should just so for denominator, if I get a real number, that is sufficient. I need to eliminate I from the denominator somehow. And I know how can I eliminate I. I just have to multiply with its conjugation. Right. So when I multiply it with its conjugation, I can eliminate I in the denominator. So I know the complex conjugate of x2 plus I by 2 is x2 minus I by 2. So what I do is I will simply multiply with its complex conjugate in the denominator. But when I do it in the denominator, I should also multiply in the numerator, right? So I should not change the value. So that is what we will do. X2 plus x2 minus I by 2. I will multiply and divide it with this particular term. If I do this way, I will get the denominator is very simple now. So it will just be x2 square plus y2 square, right? And the numerator, I know how to multiply two complex numbers. So if I multiply those two complex numbers, I will have x1, x2 plus y1, y2 plus I y1, x2 minus x1, y2. So the numerator will become this. And now you can see, right? So you separate the terms and see. So this will be x1, x2 plus y1, y2 divided by x2 square plus y2 square plus I y1 x2 minus x1 y2 divided by x2 square plus y2 square. Right, so now we got. So this is the real part that we are looking at. So this will be the real part. And this will be the imaginary part. And we have written it in real part plus I imaginary part, which is like a complex number. Right, so this is how we do division. Let's do few examples before we proceed. So see again, any concept related to mathematics, you will be able to understand when you read the theory, but you will get the sense of it, or you will properly understand when you solve problems related to it. So it is always suggested to do problems right after you learn any concept. Okay. So we have studied conjugation, absolute value, and how to divide two complex numbers. Now we will try to solve the problems related to this. So you have a complex number 3 minus 4i. Okay, so what you have to do is you have to find its absolute value, and then, okay, so before that you find its complex conjugate and then find its absolute value. Okay, so the complex conjugate, all you have to do is you take the complex number, you write the complex number, but what you have to do is instead of I, you should take minus I. That's it. So if I do that, I will get the complex conjugate for this is 3 minus 4 times minus I. It will just become 3 plus 4i. Right? So once you have this complex conjugate, I know how to find the absolute value. The absolute value square root of z bar. Right? So what will be this?
5.
5.
5.
Right. So this will be simply square root of 3 square plus 4 square, which will give you 5. So that is how you should compute the absolute values. So now you see, right? So mod z or absolute of z is not making everything positive. It's not absolute value of z is not 3 plus 4i. It is a real number. So even though your complex number is complex, okay, its absolute value will always be real. Okay. So the next thing we do is, let's say I want to divide this 3 minus 4i. I want to divide it with 1 plus 4i. Okay. So try to do this division also. So what you have to do is, when you are dividing two complex numbers, always remember that you have to somehow manipulate such that the denominator doesn't contain I. Okay, so I will write the first step, but you try to solve it. So what you have to do is, you have to multiply and divide with the denominator's complex conjugate. So 1 plus 4i's complex conjugate is 1 minus 4i, and you have to multiply the same term in the numerator also. And do this simplification, and you will know how to write this particular expression as real part plus I times the imaginary part. Okay. So these are few properties, and yeah, so small property which I left, I think. So how do I say two complex numbers are equal? So when do I say two complex numbers are equal? So that is also important to understand, right? So in real numbers, we know when will two real numbers are equal, right? So when you have a real number x1, you have a real number x2. When do I say those two are equal? When x1 is equals to x2, those two are equal. So in the same way, here also equality of two complex numbers. So if I have a complex number x1 plus iy1 and x2 plus iy2, when I say these two complex numbers are equal, so these two are equal if and only if, okay, so it's if and only if your real parts are equal and your complex parts are equal. Okay, so both should hold. So your x1 should be equal to x2 as well as your y1 should be equals to y2. So only then your complex numbers x1 plus iy1 and x2 plus iy2 are equal. So this is pretty evident. Okay, so these are some operations on the complex numbers. I hope this is clear. Let's look at some properties also. Okay, so there are certain properties using the operations that we have seen so far. And first and most important one is the absolute value of the complex number is same as the absolute value of its its complex number, complex conjugate. So the next property is, when I divide two complex numbers and take its absolute value, you can actually do the absolute values division. Okay, so this is also slightly trickier. So why I'm putting this at front is, so these are slightly trickier to understand. Okay, so but it is very easy when you substitute z1 as x1 plus iy1 and z2 as x2 plus iy2 and use all your operation knowledge, and you will get it. But in the first glance, it may not look true. But when you solve it, you'll be able to understand. Okay, so the absolute values things are slightly difficult. So even this also. So when I multiply two complex numbers and take the absolute value, is same as taking the absolute values and multiplying them. Right, so this is also an important property. So once we are good with absolute values, then all these properties are true with complex conjugates also. So when I take the product of two complex numbers and its conjugate, it will just be product of its complex conjugates. Okay, so the next thing is when I divide two complex numbers and take the complex conjugate is same as taking the complex conjugates separately and divide. Okay, and yeah, so these are few properties, and also you can write down the real parts and the imaginary part of a complex number in terms of its complex number and its complex conjugate. So the real part of z is z plus z bar by 2. In the same way, you can write the imaginary part of z in terms of z and z bar, which is z minus z bar by 2a. And how are these useful to us? How are these properties useful to us? That these are useful when you solve problems. Okay, so when a problem is given to you, we use these properties to simplify our problem. Okay, so all these properties are properties can be proven. I'm not going to prove it, but I suggest you guys to try it out. Okay, and yeah, the next is the last maybe 15 minutes I'll spend on the geometric understanding of whatever we studied. Okay, so you would have seen an R2 Euclidean space, right? So you know, when I draw these two axes, you might think that one is x-axis and another one is y-axis. But what I have drawn here is the complex plane. Okay, it's not the regular 2D plane. This is the complex plane where the x-axis is the real part, represents the real part. Okay, so real axis. So we'll call it as real axis. And the y-axis is called the imaginary axis. Okay, so real axis and imaginary axis, it's not x-axis and y-axis. Okay, so the complex plane is this. And in this particular complex plane, now I can represent any complex number. So our x1, x plus iy, which is z, which is x plus iy. Okay, so if I have to plot this, or if I have to denote that point x plus iy, I have to move x units on the real axis and then y units along the imaginary axis. So this is x and this is y. Okay, and you reach your point x plus iy. Now what is the absolute value represent? So the absolute value is the distance from the origin to the point. So this is mod z. Okay, which is square root x square plus y square. And you can see from the triangle also you form. So this is x and this is y. This is x and this is y. And this forms a right angle triangle, and I know how to compute hypotenuse. So hypotenuse will result in square root x square plus y square, which is the absolute value. So this is what I meant, distance metric. Okay, so the absolute value is this. And where will its complex conjugate lie? So this is z. Its complex conjugate will be the mirror image with respect to the real axis. Right, so it will just go to the fourth quadrant here. So this is z bar, which is x minus iy. And again, this will be y units, but on the negative side of the imaginary axis. And even this also, this is also mod z bar, which is same as mod z, right? So you can see the distance from origin to z and distance from origin to z bar, both are same. Okay, and addition and subtraction also you can visualize this. Okay, I hope so far things are clear to everyone. Okay, so the idea of complex numbers, if you are seeing it for the very first time, it might overwhelm you. But if you have seen this complex numbers earlier in your class 11, class 12, then these things are pretty elementary, should be pretty elementary to be. Okay, so when I add to complex numbers, okay, so take two complex numbers, z1 and z2. It's just like adding two vectors. Okay, so when you add two vectors, what will happen? I hope most of you know the parallelogram law, right? So it will just go to this point. It is z1 plus z2. Right, so this is how you can visualize the addition. Okay, so even the multiplication, you can multiplication, it's hard to visualize, but multiplying with a scalar. Okay, so if I have this z1 and if I multiply, if I want to look at 3z1, so that I can visualize. Right, so 3z1 will just be scaled by 3 times on the same direction, in the same direction, just like vectors. Okay, so this will be some alpha z1. Okay, and this might be some beta z2, where alpha and beta are the scalars. So in that direction only it will extend. Okay, so this is how you can visualize. And whenever we draw this axis, you just have to wait for which plane it is. Is it the real plane, the 2D plane which we so far seen, or is it the complex plane? Okay, so in complex plane, every point that you represent as x comma y is not x comma y, it is a complex number. So z1 is represented as x1 comma y1, but this is not the point. Okay, so this is a complex number and this is x1 plus iy1. Okay, so complex number, when I represent it on a 2D plane or this complex plane, it is a point, and point contains two coordinates. One is the x1 and another one is y1. So collectively, it's a single complex number. Okay, so that is very important observation. Okay, all right. So I think I shouldn't start the new things, but these are the basics of complex numbers. Okay, so these properties are really important, and these operations also you should know, and you should know the complex numbers. And what is this? Visualization is also important. Okay, so on Sunday we will see different ways of representing these complex numbers. So far we have seen every complex number is represented as x plus iy, right? So we'll also see its polar form, where a complex number can be represented as r into e power I theta. Okay, so this we will see, and then we'll see a beautiful equation. Why I say beautiful is, on the left hand side you will see everything is either rational or imaginary. Either irrational or imaginary, and even in irrational it is transludent. So kind of E, pi, and I all are very very different, right? E is Euler's number, pi is, we know, it's circumference of half perimeter of a unit circle, and I is a complex number. But if I combine these three, this will give me -1, which is an integer. Okay, so this is a beautiful equation which we'll see. So once you understand how to represent a complex number as r times e power I theta, then this e power I pi is equals to 1 is very easy. Okay, so yeah, so I think we can stop here. We'll do the remaining things on Sunday. Okay. All right then. Thanks all. Bye.
Bye.
Sir,
Thank you, sir.
Yeah.